Okay, we're going to do some related rates problems, and related rates problems are going to be no more than a fancy application of implicit differentiation. And the trick in these problems is you're going to have to get the equation set up, and then after you get the equation set up, it's just an implicit differentiation problem. Okay, so let's look at this problem here. So we're going to need, usually you're going to want a drawing, and then to get equations, and then to deal with it with implicit differentiation. So here we have a boat that's being pulled to a dock. And let's see, the rope is attached to the front of the boat, and there's a pass through a pulley on the dock. Okay, so the dock is up here, and the dock and the pulley is 1 meter higher than the bow of the boat. And the rope is pulled in at a rate of 1 meter per second. And I want to know how quickly the boat is approaching the dock. Okay, so this part is moving at a rate of 1 meter per second. And we want to know how quickly this distance is changing, how quickly the boat is moving to the dock. Okay, so this is an example of a related rates problems. We have different things that are moving here, the rope, the boat, and they're related to each other in some sense. Okay, so on our diagram, we're going to label things that are changing and things that are constant. So the 1 meter, that stays the same. The dock is not moving height above the boat at all. So the 1 meter stays the same. The things that are changing are how far the boat is from the dock and how long the rope is. So we're going to give those variable names. Okay, we're going to call this X and this Y. We are not going to put the 1 meter per second on my diagram because that's a rate and not a distance. So the 1 meter per second is how quickly the red line is changing. So that's the rate of change of y. So the 1 meter per second is telling me that dy dt is 1 meter per second. Okay. And the thing that we want to know how fast the boat is approaching the dock. So we're looking at how quickly the blue side is changing. So what we want is we want to know dx dt here when x is equal to 8. Okay. So that's the information that we're trying to find. Okay. So in this problem, we need to find out an equation that will relate x and y to each other. And so when I look at this diagram that I've drawn, the Pythagorean theorem seems like a good idea. Okay. You always want to draw a diagram when you can so that you can try and like physically see what's going on. So Pythagorean theorem, oftentimes useful, especially when we have triangles. So Pythagorean theorem here is going to say that y squared is x squared plus 1 squared. Okay. Now we're going to need to differentiate this equation because we're looking for rates of change. And so this becomes a problem just like we were doing before with implicit differentiation. So x and y are both changing with time. And so we're going to differentiate this both sides with respect to time. So we're going to get 2y dy dt is 2x dx dt. Again, remembering that x and y are both functions of time. So we take the derivative of y squared using the power rule, just the 2y, and then we multiply by the derivative of y. The derivative of 1 squared is 0. So this is my final answer, or the final derivative. We notice I can divide both sides by 2, so the 2's will go away. Okay. Now we have to plug in the information that we know. So we know that dy dt is 1. So this piece here will be a 1. We notice we don't know what y is, but we're going to need to find it. So let's leave a blank there for a second. We know that we want to know something when x is 8. So we'll plug in an 8 here. And then dx dt is the thing that we're trying to find, so it can stay there. Okay, so we notice that one thing that we need to know right now is we need to know what is y. So we want to know what's y when x is 8. So how long is the rope when the boat is 8 feet from the dock? And we can use the Pythagorean theorem again because we know the Pythagorean theorem gives us a way to relate x and y. So we can just replace x with 8. So we're going to get y squared is 8 squared plus 1 squared. So y squared is 65. So y is the square root of 65. This is the positive square root because it only makes sense to have a positive length of a rope. Okay, so that's what we're going to that's what we're going to replace y by. Square root of 65. And now we can just divide both sides by 8 to find dx dt is that was supposed to be a 65, root 65 over 8. Our units here are going to be meters per second because The distance was being measured in meters, and then they told us meters per second on dy dt. Okay. So in related rates problems, we always want to start out by finding a way to relate our various variables. So that was like the Pythagorean theorem in this case. Oftentimes to do that, we're going to need to draw a diagram. Don't start introducing variables like x and y without defining or drawing a picture that shows me what they are. And then we take a derivative using implicit differentiation and plug in the things that we know.